So today I will start with one project that is I2C. Okay, first I will tell you the means concept related to I2C, and after that we will go to the program. Okay, so I2C. So what is this I2C? I2C actually, like in the communication, there are two types of communications are there. Okay, one is like off-chip communication. Okay, off-chip communication means suppose if you want to communicate between the two ICs, okay, two ICs, we have off-chip communication. So off-chip communication is basically serial communication only. So serial communication means we need to send the data bit by bit. Okay, we need to send the data bit by bit. That is serial communication. Again, in the serial communication, there are two types are there. One is synchronous communication, and next one is asynchronous communication. Synchronous communication and asynchronous communication. Synchronous communication means what? Whatever the data is there, that will be sent synchronous with the clock. Okay, clock. So synchronous with along with the clock, synchronous with the clock, data will be one bit will be sent. Okay, and asynchronous communication means so there is nowhere related to the clock. So in asynchronous communication, mostly we will make a like make like we need to send a 8 bit of data between one start bit and stop bit. Okay, we need to make a data frame and we need to send that data. Okay, and parity bit also. Parity bit is optional. So mostly like in synchronous communication, so we will study about one is SPI, serial peripheral interface. Another one is I2C, inter-IC communication, I2C. Okay, these are the two synchronous communication. So one is SPI, serial peripheral interface, and next one is I2C. Okay, so these two are synchronous communication. Okay, asynchronous communication means basically you will study about UART. What is UART? UART is universal asynchronous receiver and transmitter. Okay, so these are the off-chip communication. Okay, and the next on-board communications are there. On-chip communication. Okay, on-chip communication. That means if you take the SoC, so system on chip, there are so many peripherals are there. The peripherals we need to communicate with different buses. There you are using AMBA protocol. Okay, so industry is mostly interested, whoever worked under this AMBA protocol, so they will, if you work under this AMBA protocol, so you will resume get highest weightage. In a year you have like APB protocol, okay, and AHB protocol, okay, you need to study about AHB protocol and AXI protocol. Okay, so this is about the on-chip communication protocols. Okay, so now we are discussing about the I2C, that is I2C inter-IC communication. So that is inter-IC communication, and this is created by a company Philips Semiconductor. Now Philips Semiconductor is NXP. Now they converted, they can change the name as NXP Semiconductor 1982, and no license is needed since 2006. So many I2C compatible device manufacturers, and this is widely used protocol. Okay, this is a widely used protocol. So basically, like I2C protocol have two buses, two lines. One is serial data line. Okay, serial data line, that is means this is bidirectional line. Okay, this is bidirectional to send the data. Okay, so here you have like master, and next you have slave. Okay, master and slave. Okay, so master can be what? It can be microcontroller or DSP processor or microprocessor. So master can write the data into the slave. Okay, what are the slave target devices? It can be like ADC or DAC, or it can be some SRAM, okay, or DRAM, okay, like that. Okay, so slaves can be some peripheral devices. Okay, Prom, okay, these are the slave devices. Okay, so microcontroller should communicate with these slave devices. So microcontroller or this master can write the data into the slave. So through which bus? HDA bus, serial data line. Okay, or microcontroller can read the data from the slave. Okay, so it can do write operation or read operation. Okay, so that means write operation means what? Write operation means microcontroller, that is master to slave. Master can write the data to the slave. Okay, that is write operation. And next read operation means whatever the data present in the slave that can be read to the master. Okay, read to the master. Okay, these are the two operations happens in the I2C protocol. So again, this is bidirectional. Remember, this is bidirectional, and the serial clock line is coming from the master to slave. Okay, so that means slave should synchronize along with the clock. Okay, serial clock is generated by the master. Okay, is it fine? Shall I move forward? This is about the I2C protocol. Mostly two lines are there. One is for serial clock and next one is for serial data line. No, no, no. Slave cannot write to the master. So master can read the data from the slave. There is some data in the slave. The data can be read by the master. Slave cannot write into the master. Okay. So this is I2C protocol. So basically, like I2C communication, there are standard mode is there. Okay, standard mode means speed 100 kbps. Actually, that in serial communication there is a term called baud rate. Okay, there is a bit rate and baud rate. What is bit rate? Bit rate is nothing but like number of bits transmitting per second. Number of bits transmitting per second. Okay, that is bit rate. Okay, baud rate is number of signals. Okay, number of signals transmitting per second. Transmitting per second. Okay, that will come under the UART also. So like IBM company, they given some standard baud rates. Okay, so like this gives the speed actually like in internet also. Suppose your internet speed is you will call like 100 kbps. Okay, so that kbps. Okay, kilobits per second, kilobits per second, and 200 mbps. Okay, this that is the what that is speed baud rate, actually baud rate. Okay, same like that in I2C you have a speed. So standard mode is 100 kbps and fast mode is 400 kbps and fast mode plus is 1 mbps. High speed mode is 3.4 mbps. Ultra fast mode is 5 mbps. Okay, these are the speed. Okay, and so basically this is a standard mode, fast mode, and fast mode plus. These are similar implementation with different timing requirements. High speed mode require controller code for high speed transfer, and ultra high speed that is write only omits some standard I2C features. Okay, so these are the different types of communication modes present in the I2C. Is it fine? These are the speeds, different types of speeds present in the I2C. Okay. Next, I2C physical layer, if you take, there are like only two communication lines per devices on the bus. I told you know there are two lines are there. One is HDA and SCL. HDA is what serial data line and SCL is serial clock line. Okay, so that means suppose this is VDD. Anyway, this is 5 volts supply voltage VDD and ground is anyway 0 volts. Okay, so these lines, these HDA lines and these SCL lines are connected through the pull-up resistors. These are the pull-up resistors. These are the pull-up resistors. Okay. So here you have multiple masters and multiple slaves. Okay. Suppose multiple masters, suppose master is there. Suppose master is there, and you have multiple slaves are there. Some multiple slaves are there. How to identify this multiple slaves means each slave has a specific address, that is 7-bit address. 7 bit to 10 7 bit, or it can be 10 bit also. By using 7 bit or 10 bit, it can identify that address. Okay, so master can identify that address and it can communicate with this slave. Okay, so I told you know like master can be what, it can be microcontroller or a microprocessor or DSP processor. So this is master, microcontroller 1, microcontroller 2, and these are the slaves: ADC, target 1. Okay, a DAC, unlock to digital converter, and digital to unlock converter. So these are the target devices or slaves, we can call as slaves. Okay, so basically like in communication there are three types of communications are there. One is half duplex. Okay, simplex, sorry, One is first one is simplex type of communication. Okay, so simplex communication means what? Only one way communication. Like suppose broadcasting is there. So broadcasting means you are getting the signals from the satellite or stations to TVs. Okay, TV cannot send the data, no, like that. Suppose if you take a PC or your laptop and PC and printer. Okay, so PC can give the signal to the printer. Printer can't give the signal to the PC, no. So only one direction the data can be transmitted. That is simplex. Okay, and next you have half duplex. Half duplex means two-way communication. Okay, so from transmitter to receiver or from receiver to transmitter. Okay, receiver to so this is transmitter, from the receiver to transmitter, but at a time either transmission can happen or it can be receiver can happen. Okay, like walkie talkie present in the traffic police. So one police will talk. Okay, after speaking that police, after that other person can speak. Okay, so this is what this is bidirectional half duplex. That means any one time either transmission can happen or receiving can happen. Sorry, both cannot happen in the same directions. Okay, both cannot happen in means same direction, means parallel. So at a time either transmission can happen or receiving can happen. Okay, and next you have full duplex. Full duplex. Full duplex means what? Both transmitting and receiving happens parallelly, same time. Like your mobile phone is there. Okay, so your mobile phone, so both can speak parallel. So transmitting and receiving will happens at the same time. Okay, so example is basic example is your mobile phone. Okay, or your telephone. Okay, that is a full duplex communication. These are the three types of communication having are there. Okay, so basically this I2C is what? Bidirectional communication. Either that means what? Master can send the data or write the data, or slave can means master can read the data. Okay, at a time write operation means either write operations can happen from master to slave, or it can read operation will happen from that means from slave to master. Okay, either it can be write operation or read operation. Okay, so and it allows the multiple controllers and multiple targets, and it require pull-up resistors on both SDA and SCL. Okay, so why pull-up resistors means when it is connected, so this through the pull-up resistor, this SDA will go from high to low. Okay, after that SCL will go from high to low. Okay, so when it is going from high to low, so then the device is connected. Okay, that is start condition we'll discuss. So that is so how it is going from high to low means through the VDD and through the pull-up resistor, it is going from high to low. Is it fine? This is the I2C physical layer. Okay, so actually like in the I2C physical layer, there is a open drain connection. Open drain connection means here VDD is there, pull-up resistor is there, and these lines are what? There are two lines are there, no, HDA and SCL. These are the two lines. Okay, so HDA and SCL, these are the two lines are there, and these are connected to my I2C device. Okay, either it may be master or slave through the fast transistor, through this fast transistor. So what is my fast transistor? Basically this is NMOS transistor. Okay, so that means when it is connected, that means when it is VDD is connected, so when I2C through this I2C device, one is giving to this NMOS transistor. So when one is giving, this NMOS transistor becomes on. Okay, so when NMOS turns on, what happens? This will be shorted. Okay, so my SDA and SCL will pass from where to where? From VDD to ground. So that means it will be pulled low. Okay, it will be pulled low. Okay, so this is the quick transition from high to low, as NMOS pull charge from any bus capacitance from SDA to SCL. But when you release this your device, okay, when it is going from low to high, so means there is no quick transition. There is some exponential increase. It will go from, so here it is go from high to low, and here there will be some exponential increase. It will go from low to high. Okay. So this is basic open drain connection. What is this open drain connection? Okay. So I2C have a open drain connection. Okay. So that means whatever the when it is going from low to high, it is a exponential increase. Okay, exponential rise. That depends on the capacitance. Okay, internally there will be a capacitance on HD and SCL, and also there is a pull-up resistor is there. It depend on my RC value that exponential rise will be there. Okay, so this is about the open drain connection. So basically there are two types of physical layers are there. So one is open drain which I explained. Okay. So and next one is push pull configuration. Okay. So push pull configuration means you are using this CMOS circuit. Okay, you are using this CMOS circuit. That means PMOS has pull up and NMOS has pull down. Okay, so uh, so open drain output can connect it together. Any output that goes low will pull the bus low. Okay, so if any output will go slow, that pull the output low. Okay, this type of connection is what wide OR we call as wide OR. Okay, and coming to the push pull configuration, open drain output cannot connect together. Okay, open drain. Sometimes suppose this will go to high, sometimes this will be on, this will be off. Okay, so that means it will not go to low, it will be open only. So suppose this will be short circuit and this will be open circuit, there is no connection. Okay, here what happens, sometimes this will be off. Okay, so this will be off and next this will be on. Okay, so there will be no connection between VDD to supply voltage. Okay, so when you consider the open drain connection, when the device will go to high to low, so that means HDA and SCL will go from high to low. Okay, so basically we'll prefer in the I2C, we'll prefer open drain connection compared to push pull connection. Okay, so this is I2C physical layer. Is it fine? Shall I move forward? Okay, yeah. So in this I2C, there are first start and stop condition. Okay. So what is start condition? There are two lines are there, no? So SDA, serial data line and serial clock line. Okay. So in start condition, what happens? In start condition, first initially when device is not connected, these HDA and SCL line will be high only. Okay. So when both are high means what? So here VDD is connected. VDD is actually it is connected through the pull-up resistor, and this is not connected to the ground. So when it is not connected to the ground, basically when it is in idle state, this will be two lines will be what high only. Okay. So when those are connected, start condition. Start condition means first HJ should go from high to low. After that SCL should go from high to low. Okay. So that means a controller claims the I2C bus. Okay. What are the I2C bus? HDA and SCL. Okay. So claim the I2C bus for communication with the target device. Okay. How to claim? First HDA should go from high to low. After that SCL should go from high to low. Okay. This is the start condition. Okay. And after that stop condition. I2C stop condition means what? First SCL will go from low to high. Okay, so this is high to low. First it will go from high to low, and after that next it will go from high to low. Okay, SCL will go from high to low. That is start condition. Stop condition means first SCL will go from low to high, and after that SCL HDA will go from low to high. This is stop condition. Okay, so that means controller device completes communication with the target device and release the I2C bus. Okay, after communication, after doing some write operation or read operation, so that means it should release the I2C bus. Okay, How to release the I2C bus? First it is making SCL to go from low to high. After that, it is going from HDA to go from low to high. Is it fine? This is the start condition and stop condition. Okay. Next. Next. Logic ones and zeros. So normally, like this is HDA line and this is SCL line. Okay. So HDA line is what data line and SCL is what serial clock line. Okay. So we'll send the data through the HDA line. Okay. And we'll send the clock through serial clock line. Okay. So HDA only transitions when SCL is low. So when the HDA will transmit the data, when the SCL is low only, then the data will be transmitted. Okay, except during start or stop condition. So when the data will be transmitted, when SCL is low only, then that whatever the data is there, that is transmitted from either it may be 0 or 1. So it will be transmitted from the master to slave, or it can be read from the slave to master. Okay, so HDA is high when SCL pulse is logic 1 and HDA is low when SCL pulse is logic 0. Okay, these are the so basically what you need to remember means the data, whatever the data is transmitting through the HDA will be transmitted. So if you want to transmit 1 or 0, that will be transmitted during when SCL is equal to 0. Okay, when SCL equal to 0, the data will be transmitted. Okay, so this is logic ones and zeros. So this is the basic timing diagram. So this is the address frame. First, this is start condition. I told you start condition, no? So what is the start condition? First, SDA will go from where to where? High to low. It will go from high to low. And after that, SCL will go from high to low. Okay. Second, SCL will go from high to low. Okay. So after that, so I told you, like master, suppose one master is there. Okay. Some different, some like three slaves are there or multiple slaves are there. So that means master should communicate with any one of the slave. Okay. So that means how to communicate means each, let us take this is slave 1 and slave 2 and slave 3. Okay. Each slave has 7-bit address. Okay. 7-bit address. Okay. So first, through the decoder circuit, master will generate the address. Okay. So for which slave it should communicate. Okay. Suppose it want to communicate with slave 2. Okay. So first it will identify the 7-bit address. Okay. And it will make the connection between this master and slave 2. Okay. By identifying the address only. So without address, how you can communicate with the slave? Okay. So that means there is a mismatch. Okay. Master cannot identify the which slave it is communicated. There is some address will be there. Okay. So that is 7-bit address. Okay. This is what A6, A5, A4, A3, A2, A1 and A0. Okay. So this is what a 7-bit address. Okay. 7-bit address. 7-bit address, that too sending 7-bit address is there, no? 7-bit address, one second. 7-bit address is 7-bit A6, A5, A3, A1. Okay, that is sending when SCL equal to low. See here, when SCL equal to low only, that address is transmitted. Okay, and after that there is one more signal, that is read by write bar signal. Read by write bar signal. I told you, master can write the data to the slave. Okay, from master to slave, or master can read the data from the slave. Okay, so when read by write bar signal equal to 0 means it can do which operation? Write operation. Okay, when read by write bar equal to 1 means it can do read operation. Did you understand? It can do write operation or read operation. Okay, so it can do write operation or read operation. Once again, yeah. So it can do write operation or read operation. And next there is so here I see here. This is the start condition. Start condition means what? HD should go from low to high, and after that SCL should go from low to high to claim the bus. Okay. So this is start condition. And next 7-bit address is there. 7-bit to make the I2C address. So master should identify the address, 7-bit address. And next, read by write bar signal. So this read by write bar signal indicates the direction of communication. So that means if it is 1, controller wants to read the data from the target. So that means read by write bar equal to 1 means what? So means the master should read the data from the slave. Okay, it should do read operation. Okay, so if it is when read by write bar equal to 0, then master master should write to the target device. That means it should write the data to the slave. Okay, it should do write operation. Okay, this is read by write bar. Okay, and after that there is a acknowledgement. Okay, so when acknowledgement occurs, HDI is pulled down as ACKT. There is an ACKT. ACKT means what? Acknowledgement target. Okay, acknowledgement target. Okay, so like suppose how is this acknowledgement means? Suppose like let us take one wall is there. Okay, just practical examples, real time practical examples I will tell you. Just two persons are there. Okay, two persons are there, and this person is throwing some box from here to here. Okay, so every time when he is throwing the box, he should be attentive now. He should be attentive. Okay, so suppose like there is a mutual understanding that this person will tell within 2 minutes he will throw the box. Okay, for every 2 minutes he will throw the box. Okay, so like that means every 2 minutes he will be attentive. So within the 2 minutes he makes relaxed. Okay, so there is a mutual understanding between two persons like this. Okay, so like that there is a master want to write the data to the slave. First it will send the acknowledgement. Okay, suppose like post letter if you are sending the post to your neighbors or friends. So how you can know that that letter is received to the neighbor? Just in olden days there will be acknowledgement letter. You will post along with the that letter, and that will be sent again. If you receive that acknowledgement letter, you can clarify that is received to your friend or neighbor. Nowadays so communication has developed. Then now you after receiving, your neighbor will call, neighbor or friend will call that I received that. Okay, so that is one type of acknowledgement. Okay, similarly in the WhatsApp also, just if you are sending the data, if you are sending the message to your friend. Okay, so if you are getting one tick means what? What you can understand? You can understand that your friend not read the message. Okay, if you are getting two tick with blue line means what? So you can understand that your friend has read the message. Okay, so like that master will first it will send the ACKT. Okay, ACKT to the slave, whether slave is ready to receive the data or not. Okay, or whether slave is ready or not. Okay, that is what ACKT. Okay, HDI is pulled low or ACKT, acknowledgement target, after address byte, target device ACKs the communication. Okay, first master will send the ACKT to slave, whether slave is ready or not. Okay, so that is first acknowledgement. Okay, and after that, suppose slave will tell that I am ready. Okay, so after slave is telling I am ready, so master will send 8 bits of data. Okay, this is data frame. Okay, single byte communication. Okay, serial communication means what? Single byte communication only. So 8 bits you will send a bit by bit. Okay, that is serial communication. Bit by bit it will be sent to the master, from the master to the slave. Okay, so that means this bit will be sent during the active low of the clock that we already discussed now. During this active low of the clock only this data will be sent. Okay, this data will be sent. Okay, so after 8 bits of data, again one more acknowledgement will be there. Okay, one more acknowledgement follows the data frame. Okay, suppose suppose master is doing the write operation. Okay, master is doing the write operation to the slave. Okay, so after writing the data to the slave, master should verify that the data is received to the slave or not. Okay, So write to the target. That means ACKT. One more ACKT is there. Write to the target. Come from the which device? Target device. That is master. Okay. And one more read signal. That means for read operation. I told you, no, master can do the write operation, or master can do the read operation from the slave. Okay. So when it will do the read operation, so read from the target. Okay. So that means so AC, one more ACKC is there. ACKC comes from the controller. Okay. So that ACKC is there. No, ACKC comes from the controller. That controller will say that I read 8 bits of data. Okay. If it is read operation, we will get ACKC. If it is write operation, so that is ACKT. That is comes from the target. That is slave. Okay. ACKT. There are two types of acknowledgements are there. Is it fine? Do you understand? Shall I move forward? No, no, it will not send. Yeah, acknowledgement is not coming means so that means it will wait for some more time and again keeps on sending the acknowledgement. When the slave is ready, then only it will send the data. Okay. Again, next is stop condition. So what is stop condition? First SCL will go from low to high. After that SDA will go from low to high. Okay. This is the basic timing diagram of I2C protocol. Okay. So these are the some questions. So before address frame I2C, what action make up the start condition? Start condition means SDA will go from high to low, and after that SCL should go from high to low. So that means controller sets HDA low and then sets CL low. That is start condition. And in address frame, after controller device sends 7 bit of data, what is the next part of I2C protocol means read by write bar. Controller sends read by write bar bit to indicate what operation it want to do. Either it should write the data to the slave, or it can read the data from the slave. Okay, that operation will be done. And because of NMOS open train controller to SJ to SCL, which part of the communication waveform is faster? That means when it is going from, as this is open train, NMOS open train communication, it is going from high to low will be faster. Fall time of SDA and SCL will be faster. Okay. Rise time is slower only. Exponentially it is increasing. Depends on the resistance and capacitance of internal device. What is the benefit of having open train connection over push pull means this will prevent the destructive current draw during the bus contention when output are tied together. So this is about I2C concept. Any doubts or queries? Yes, yes, yeah. For every one cycle, one bit of data will be serial communication. No, serial communication means one bit will be transmitted. First, I told you like off-chip communication is a serial communication. If you take SPA and I2C, that means I2C have two buses. No, like you have two lines. SPA you have four lines. One is MISO, MOSI, and one more serial data line and clock line. Total four lines will be there. That is SPA, serial peripheral interface. And UART is one type of other communication. There is no clock in the UART. Here we will send 8 bits of data. This is 8 bits of data with one stop bit and one start bit and one stop bit. It can be either 1 or 0 depending on that. We will make an address frame and we will send it to that. And at the receiving, what we will do, we will compare with the start bit and stop bit, and we will verify that proper data is sent or not. That is one type of communication. Yeah, yeah. The speed is depends on the frequency. Yeah, speed is depends on the frequency. Yes. Shall I move forward? So we'll go with the programming part. So there are two types of operations are there. This is I2C master. I2C master means I can give this name as I2C master underscore write operation. Okay, I can give this name as write I2C master write and I2C master read. Okay, so this if you see the I2C master write, so if you see the I2C master write, first this is simple I2C master write only demo. Generates start bit and sends 7-bit address and a read by write bar signal and one data byte and then stop it. Okay, so here what is my module name? I2C master. Okay, input wire clock, that is the system clock. Input wire reset underscore n, this is active low reset, and input wire start. Okay, this is triggering the transaction. And slave, I told you slave is 7-bit, no? So I need to declare with wire 6 down to 0 address, and the data is the 8-bit. Okay, input wire 7 down to 0 data byte to send. Okay, output, so clock is from master to slave, no? That is output. Okay, so output reg is SCL is serial clock line. And there is one more HDA. I told you HDA is a unidirectional or bidirectional serial data line. Yeah, bidirectional. That's why I'm declaring with what in out. It can be act as input or it can be act as output. When your master is doing the write operation, it is acting as output. When master is doing the read operation, it is acting as the input coming from the slave. Okay, so that's why I declared with in out via HDA line. Okay, serial data line. And one more output I am declaring, that is busy. Okay, so busy means what? Suppose when busy flag equal to 0, so means master I2C bus will be idle state. Okay, when busy flag equal to 1 means what? I2C is said to be in busy state. Okay, so I told you, know, like you have multiple slaves are there. Okay, suppose when master is communicate means I2C bus is used by one master and one slave, and other slave want to communicate or want to use that I2C bus. So first it will check for the busy flag. So when a busy flag equal to 0, then it can use that I2C bus. When busy flag equal to 1, then master or slave, it can identify that, it can understand that that is busy with some other that I2C bus is busy with it is communicated with some master and slave. Okay, that is busy flag. And next you need to declare reg 3 down to 0 state and reg 3 down to 0 bit count. This is bit count, this is 4-bit. And one more reg HDA underscore out, HDA underscore enable. Okay, this is also enable. Okay, as this is open drain HDA, so open drain HDA, you need to declare assign HDA equal to HDA enable. Okay, HDA enable, then HDA out is assigned to HDA, otherwise it will be in the high impedance state. Okay, okay, so that means when it is HDA is pulled low, that means when HDA, when it is pulled, when it is connected, HDA connected to that either slave or master device. So in that situation, HDA is connected, HDA out is connected to HDA. Otherwise, that will be in high impedance state. That HDA line is in open drain condition. Open drain means what? Open state. That will be like we can call as open circuit. That is high impedance. We call as Z means what? High impedance. Okay. So when it is connected, HDA out is connected to HDA. Okay. And I am declaring with local param. So local param means this is related to this code only. Okay. So local param. How many states I am using? 6 states I am using. So idle state, that is 0, start state is 1, address state is 2, and acknowledge, I told you two types of acknowledgement, acknowledgement 1 and acknowledgement 2. So acknowledgement 1 is 3 and data is 4, acknowledgement 2 is 5 and stop is 6. Okay. So always at the rate passage of clock or negate of reset begin. Okay. So this is what type of reset I told you. This is asynchronous active low reset. Okay. With respect to reset, there is a long discussion on this. Okay. So when you indicate reset in the sensitivity list, that we call as asynchronous active low reset. Okay. This is active low negate. Okay. When you are not indicating means, so that becomes the synchronous reset. Okay. So begin if not of reset. If reset equal to 0, so when reset is applied, what is the state? Initial state, it will be idle state. Okay. Initially SCL will be 1 and SDA out. Okay. SDA is initialized to SDA. No. SDA out equal to 1 and SDA enable is equal to 1. Busy flag. So that means there is no bus is connected. So busy flag is what? 0 and bit count is also 0. These are all our initial values when power on reset. Okay. I2C when power on reset. Okay. Else begin. I am using case statement. Okay. That is when it is idle state, begin SCL equal to what? 1. Okay. SDA out equal to 1 and busy equal to 0. Okay. So if start begin, busy flag becomes 1 and what is the next state? Next state will be start state. Next state will be what? Start state, end and end. Okay. So this is the idle state. Okay. And coming to the start state, I told you. So start state, we need to make first SDA from high to low. Okay, start, begin. So I am making SDA out equal to 1 tick binary 0. This is start condition. And what is the next state? Address. I want the slave address. Okay, next state equal to what? Next state equal to state, that state equal to address. And what is the address length? 7 bits. Bit count equal to 7 bits. Okay, so start state, we need to declare this. And in address, begin. So in the address, I need to make SCL to low. Okay, first SDA to low, and in the address, I need to make SDA to low, and SDA out equal to what? You need to get the address bit count. Okay, and during that state, SCL I am making as 1. If bit count equal to 0, begin. Okay, so bit count means what? 7, 6, 5, 4, 3, 2, 1. Again, it becomes 0. Okay, that also address also will go from bit by bit. So bit count becomes 0 means what? What is the next state? So it is identifying the slave address. 7-bit address it is identified. Next state it should go to the acknowledgement. Okay. So master should identify that whether slave is ready or not. Okay. So how it is identifying? By giving the acknowledgement to the master. Okay. So that is state equal to what? ACK1. Okay. Next state equal to ACK1 and SDA I am making as low. Okay. This is the right bit. Okay, SDA out is equal to write bit. So master should write the data, no? Read by write bar signal. Master should write the data. Else we need to decrement bit count equal to what? Bit count minus 1. Okay. So this is for what? Address. Okay. And coming to the ACK acknowledgement. So STL should be low and SDA enable should be low. We need to release SDA for ACK and SCL I am making as 1 and next state is data and bit count is 7 and SDA enable equal to 1. Okay, this is for ACK acknowledgement. Okay, and coming to the data, in the data SCL I need to make as 0 and SDA out equal to what? Data bit count. Okay, 8 bits of data that is coming to the SDA out. Okay, again I am making SCL equal to 1. Okay, so if bit count equal to 0, so every time it will be decremented. No, bit count equal to 0, next state is ACK2, else bit count equal to bit count minus 1. Every time this will be decremented. This is for 8 bits of data. Master is sending 8 bits of data, 1 bit to the slave. Okay, and after that, master is verifying whether the 8 bits of data is sent to the slave or not. How it is sending? One more acknowledgement it is giving. That is SCL equal to 0 and SDA enable I am making as 0, release SDA for ACK and SCL I am making as 1. Okay, if you see the timing diagram, they based on that only I wrote. Okay, and what is the next state? Stop state and SDA enable equal to 1. Okay, so you need to release SDA means what? You need to make SDA enable equal to 0. After that, you need to make SDA equal to 1. Okay, so this is for ACK2 and stop condition means what? Again In the stop condition, first SCL will go from low to high. After that, SDA will go from low to high. Okay. So first SCL will go from low to high. Okay, that is stop condition. And SDA out will be 0. After that, SDA out will be 1. This is stop condition. Okay. And what is the state? After stop condition, it will come to the idle state. So when it is coming to the idle state, busy flag becomes 0. So when busy flag becomes 0, so other masters and slaves can use that I2C bus. Okay. When busy flag equal to 1, during this what state, start state, address state, acknowledgement state, data state, or acknowledgement to state, okay, busy flag will be 1 only. Okay. So when busy flag equal to 1, other masters and slaves can't use that I2C bus. Okay, they can understand that that is busy with connecting with other masters and slaves. Okay, is this code is fine? Did you understood any doubts or queries? Okay, so based on that understanding only, I wrote the code. One second. Coming to the test bench, so I wrote for the master TV master. Okay, I can change to write underscore write. Mm, Here test bench is same only, that 5 steps are there. First you need to declare module TB I2C master. So you need to declare clock reset underscore n and start with reg data type and address 6 down to 0 vector, that is 7 bits. Okay, that is address, slave address, and reg 7 down to 0, that is data. And I need to declare the wire SCL, wire SDA, and wire busy flag. These are the internal variables of the test bench. Okay, internal variables of the test bench. Okay, and I need to instantiate my design in the test bench. How to instantiate a design name? What is my design name? I2C master, and instance name UUT, and this is connection by name. Okay, we already discussed this connection by name also. And next you need to generate the clock. Okay, how to generate the clock? Initial begin clock equal to 0 forever #5 clock equal to not of clock. Okay, this is generation of clock. And initial begin, as this is asynchronous active low reset, first I am applying the reset. Okay, as reset underscore n equal to 0 and start equal to 0. So address, what is the slave address I am giving? 42. 42 means what? 70 H42. So how it will take 100 0010, 7 bits it will take. Okay, so that last bit it will not take, 7 bits it will take, 100 0010. Okay, that is the slave address. And data what I am giving 8 tick HEA5. Okay, and after 20 time units I am deasserting the reset. Here I am asserting the reset. Okay, here I am deasserting the reset, and I'm triggering the start condition. Okay, triggering the transaction. Start I am making as 1. After 10 time units, I am making start equal to 0. I am running for how many cycles? 500 time units. I am seeing the simulation. Okay, and if you want to execute in the EDA playground, you need to use these two commands. $dump file I2C master.vcd, $dump wires 0, tb, I2C master. If you are using Vivado, no need to use that commands. So just I want to show the output. It will take time to open. Yeah. Go to the file, project, new project. Next, what is my project name? I2C